Good evening, everyone. I'm Chandra Kumari Kalla. Today, I'll be talking about neural networks to approach optimal receivers for high-speed optical communication. I would like to acknowledge my co-authors Rizan and Sasan and my professor Leslie and Rush. We are coming from COPL Laboratory in University Laval, Canada. This is the outline of my today's presentation. First, I'll be talking about the memory effects caused by the intersymbol interference in the band limited channels and how mitigating them would allow us to reach high-speed optical communication. And then I will be giving a brief about conventional optimal receivers like MMSC and MLSC and few of the limitations and how neural network could serve as a possible solution to mitigate this ISI. We examined three architectures in this paper for ISI mitigation, the linear multi-layer perceptron, non-linear functional neural net, and long short-term memory recurrent neural net. In the results and discussion section, we would compare this neural network architectures with respect to the conventional optimal receivers, and then I would have some concluding remarks. Let's get started. So the intersymbol interference is the channel distortion effect that's caused because of the spreading of the pulses in the time domain, and each symbol interference with the other symbol, and at the detection end we have the past and the future symbol memory into the present symbol, and because of this we observe the increase in the bit error rate values, and the power penalty severely increases for the reliable transmission. In the optical domain, this pulse spreading is mainly caused because of the chromatic dispersion in the optical fibers or because of the band limitation of the channels. But today we would be focusing on the pulse spreading that's caused because of the band limitation of the channels. So in the high-speed optical communication, the system devices are highly band limited, and when we are targeting very high bit rates, signal bandwidth increases. And when this high bandwidth signals pass through the band limited devices, we observe a severe attenuation of the higher frequencies, and this leads to the pulse spreading and the intersymbol interference in the time domain. Despite the Nyquist signaling, due to the high band limitation of the channels, this ISI still remains and increases the bit error rate values. There are few ways to mitigate this ISI. One way being post-compensating or equalizing the received symbols at the receiver end. There are a few conventional optimal receivers in digital signal processing. We have minimum mean squared error with a low complexity. It is a linear equalizer. And then we have a very effective and excellent solution provided by maximum likelihood sequence estimator, but this estimator is highly complex. We will look into this equalizers now. This is the typical communication block diagram. We have the transmitted symbol that passes through the channel, which induces the ISI into it. And at the receiver end, we have the additive white Gaussian noise added to the transmitted symbol. And we have the MMSC equalizer or any post-compensation equalizer that tries to mitigate the ISI. And here the MMS equalizer is trying to minimize the mean squared error at the output, and it tries to have the equalized output as close to the transmitted symbols. But there are few limitations for this MMSC equalizer. The performance of the MMSC equalizer severely depends on the channel frequency response, and it decreases severely when the channel response is bad. Suppose if we have the spectral nulls in the frequency domain, or in our case, if we have the high band limitation of the channels, the MMSC performance is severely deteriorating, and when we are targeting very high bit rates, the severe attenuation of the high frequencies increases a lot, and then the MMSC solution wouldn't be much reliable. So moving on to our next optimal equalizer, we have MMSC equalizer that provides very efficient solution using the trellis architecture to mitigate the ISI. This finds the most probable sequence. Unlike MMSC equalizer, which targets only on the present symbol, this focuses and outputs the most probable sequence depending deciding on the all sequence information. But there are few limitations even for this MLXC equalizer. The first and the main limitation being it requires a complete channel state information, which should be accurate. If there is an error in the channel state information, the MLSC equalizer performance severely deteriorates and it diverges from the optimal solution. And the second and the most important limitation being the implementation cost of MLSC. The complexity of the computational complexity of the MLSC equalizer increases very exponentially with the memory length and the modulation order. And in the high data rate communication, we always target the high modulation orders, and the ISI impact could increase. So the complexity of this MLSE equalizer would quickly become practically infeasible. Recently, neural networks have shown great potential to learn the channel indirectly from the data without the explicit CSI. And in this paper, as we have discussed before, we examined 3 neural network architectures that replace the post-compensation block in the communication system. We'll soon see that the linear multi-layer perceptron approaches the MMSE equalizer solution, whereas our 2 nonlinear architectures would approach the MLSE equalizer solution. Going on to our first architecture, we have linear multi-layer perceptron, which is a simple feed-forward neural network. And we have 3 layers: input, hidden, and output layer. The input layer is having 58 features with 15 past and 15 future and 1 present symbols IQ, in phase and quadrature phase component. And the output layer has equalized INQ. And each hidden layer has, the hidden layer has 70 neurons. Each neuron is a linear convolution block of the weights and the inputs. All the weights of the neural network are adopted to decrease the mean squared error at the output. And we use the stochastic gradient descent algorithm for all the neural networks that we have examined in this paper. This simple linear neural network solution approaches only MMSE but not MLSE. We concentrate on our 2 nonlinear neural net architectures to approach the MLSE. So the first nonlinear neural net architecture that approaches the MLSE is NLFLN. We have to remember that MLSE feedbacks on the previous decision and outputs a sequence which is showing a nonlinear behavior. So our first architecture focuses on the nonlinearity instead of the feedback, and this nonlinearity is imposed in the form of the tan H. So contrast to our linear multi-layer perceptron, NLFLN has 2 hidden layers with the nonlinearities in form of tan H, and we have input layer with 18 features consisting of 4 past, 4 future, and 1 present IQ. And the output layer is similar to the previous architecture. It is equalized INQ. And each hidden layer has 15 neurons. And this concatenated nonlinearity helps us to capture the better output and input relationship, and also helps us to capture the nonlinear nature of MLSE. Soon we'll see that this architecture approaches the MLSE solution. Moving on to our next and last architecture, the LSTM. The optimal MLSE performance is achieved by examining into a long sequence of previous symbol decisions before outputting a sequence. So our last architecture focuses on the feedback path to achieve the similar visibility and approach the MLSE solution. Contrast to LMLP, the RNN architecture has cell units, and each cell unit is having an additional memory block that allows it to have remember the past information. So the input data is combined with the past information and does the sequential processing. This is a typical LSTM RNN architecture in the figure here. We have 3 layers: input layer with 18 features and the output layer with equalized IQ. The hidden layer has 70 LSTM units. We can see that each LSTM unit has a memory cell to maintain the past information, and at each time step we have the past information combining with the present input to calculate the present output. The simple difference between LSTM and LSTM and an RNN cell being the LSTM cell has forget, update, and output gates that allows it to remember and forget the information from the past, allowing it the complexity of that LSTM cell to capture the long-term dependencies much better. So let's move on to our results and discussion section. We have examined 2 channel responses. One is the proACUS channel, which is shown in blue dots here, and other is the other is the silicon photonic channel shown in the red lines here. The proACUS channel is a typical wireless channel, and it has high band limitation because of the severe multipath fading. And whereas the optical channel is estimated from the experimental system response of a 100 gigabaud system that goes into a 35 gigahertz silicon photonic modulator. This is representing a typical silicon photonic optical system. And we have compared the neural network architecture performance with respect to optimal solutions in terms of bit rate performance versus SNR over 10 power 5 symbols for the 4-QAM transmission. Here we can observe that the bit rate values of the proACUS is higher than the optical channel without the equalization, because the proACUS channel is having much higher band limitation. When we see the solutions provided by the optimal receivers, we observe the high penalty or gap between the MLSE and MMSE equalizer for both the channels. This is because of the band limitation of the channels. And presenting our first linear solution uh, in red diamonds, it is coinciding with the MMSE solution for both the channels. And our nonlinear solutions, the first one being NLFLN shown in the red circles, and the second one being the LSTM RNA shown in the red solid lines. Both these solutions are converging to a similar solution to the two different channels, and both of them are outperforming the MMS equalizer. When you observe at the 7% fact threshold, these two solutions are having very small power penalty compared to the MLS equalizer. In fact, it is 1.9 dB for Proikis channel and 1.2 dB for optical channel. And it should be remembered that this is the optimal performance of the MLSC with perfect CSI. And when there is error in the CSI estimation, the MLSC performance can severely deteriorate. And at 7% fact threshold, despite of the large gap between MLSC and MMSC in ProIKS channel compared to the 6 dB gap in optical channel, both the nonlinear equalizers have a severe power penalty, and it is worthy to be noted. Moving on to our last concluding section, we have introduced and presented two neural network architectures, and LFLN and LSTM-RNN. These two nonlinear neural nets approach the perfect CSI-MLS equalizer. At 7% fact threshold, they have less than 2 dB power penalty. And in contrast, we have also examined the linear neural net that achieves only MMSE performance. The two nonlinear neural nets have different features. One, NLFLN is having in terms of nonlinear activation function, and LSTM in the terms of feedback architecture. Both have a severe improvement over MMSE but couldn't achieve MLSE performance. But when we are targeting very high bit rates or high modulation orders and and when we face higher ISI impact, the NLFLN may offer better scaling opportunity, whereas MLSE complexity increases very exponentially with QAM order and ISI memory length. I'd like to acknowledge our industrial partners, Huawei Canada and NSERC. Thank you for your attention, everyone.